Welcome to this FMSP online revision video for the MEI Differential Equations module, or the DE module. This video will cover the simultaneous second-order differential equations. Actually, they're simultaneous first-order differential equations, and they turn into a second-order differential equation. But it ends up using the same skills as you used to solve second-order differential equations in general, so this is actually more of the same. It's a very predictable type of question. It almost always turns up as question 4 on the exams, although not necessarily. And it is a predictable layout, so we're going to look at one particular example as our way through. It is also worth reminding you that on the DE paper there are always 4 questions, and you only have to do 3 of them to get full marks. They will take the best 3 questions that you attempt. That may mean you try all 4, it may mean you select one to not have a go at, but only 3 will get you the marks, and therefore, since everything's out of 72, each question is exactly 24 marks. That's worth recognizing. So you always have a choice to do this sort of question. Almost always will be there, like the example we're going to look at. But you can choose to ignore it, like all the other questions. To be honest, this one's the more predictable of many. Let's have a look at what the specification says. They mention these simultaneous linear differential equations, and they point out that these are situations where you have one independent variable and 2 dependent variables. Usually this will be time, and usually this will be x and y. There's no reason it has to be those particular letters, but they often use that. So you have actually first order simultaneous differential equations. One involving x dot and one involving y dot typically, and you can combine the two to end up with a single second order equation, and then all your second order skills come into play. That's pretty much the principle every time. They do mention actually that you need to be recognized that this same method can be used to have more than 2 variables, so maybe you have a z variable as well, in which case when you try and eliminate 2 of them you end up with a higher order equation. In this case it would be a third order equation. And since they do mention that you can solve third order equations using the second order method that you're used to, as long as they guide you through it, they could ask you one with this. A couple of things to mention though. They note a particular application of these simultaneous things. So quite often foxes and rabbits are used as an example. Maybe X is the population of foxes and Y is the population of rabbits, or something like that, and they would depend on each other because one eats the other and so on. And there would be linked differential equations which you could reduce to one second order equation to solve it. So this predator-prey idea is a very important example of these things. Furthermore, they point out again that if they're going to ask you to extend it to a higher order thing, they will give you what they call adequate guidance, i.e. they'll tell you how to do it, which is a relief. Although, to be honest, even if they didn't, I suspect with a bit of practice you wouldn't have a problem solving them anyway. We're going to look at this by looking at one example. In fact, we're going to look at June 2010 question 4, because it's pretty typical of these. This is the most predictable type of question in DE. They're not necessarily easy, but they are relatively predictable. So let's have a quick look at the overview of this question. This question is pretty typical then, so they start by giving you 2 first order equations. Notice these are first order because of the dx dt, no higher derivatives there, but this dx dt also involves this variable y, which is not otherwise mentioned in this equation, and they also give us then a similar first order thing for dy dt. So this is different from some of the other first order things you look at because there are 2 variables other than x and t. There's an x and a y and a t instead of just an x and a t. So we have to combine them to get there, and they almost always ask you to do that. In this case, they even tell you which one they would like. They're implying that they want this equation with x's and t's only, so you're kind of thinking we need to eliminate y. Some questions won't say which one they want. They say get a second order equation out of these 2, in which case you have a choice about which one to eliminate. And it's worth getting into a routine for how you're going to eliminate one of the variables and do it the same every time, so this becomes a predictable routine. Almost always they ask you to then solve that second order differential equation. Please notice if you fail at part 1 to get that, show that you could still do part 2 and there are more marks available. So don't ever give up. If you can't do part 1, you can still continue and solve that equation, assuming that it's correct. Almost always, once you've got an equation for one of the variables, in this case x, they will ask you to find the corresponding solution for y, and you can use part 2 to do that. Again, almost always they then give you some more information. In this case, just the fact that at t is 0, that's what initially means, x is something and y is something, which lets you find particular solutions. And finally, almost always they ask you to describe some sort of behavior of these solutions. In this case, they're asking for a description as t gets really large. What happens in the long term? There's almost always some sort of description, maybe a sketch to do in the last part of these questions. Let's work our way through it as an example of how to solve them though. So part 1, we need to get rid of one of these variables. In this case, they've told us, as I mentioned, to get rid of get rid of y, because this is an equation with x and its derivatives. I would quite often write eliminate y just to get my head around it. And I would also point out that it's worth writing down in your own notation these equations, and that forces you sort of get your head into the question a bit. So I'm just going to copy them out. I know this is slightly strange just to see me writing out something right next to it, but it's a good piece of advice, I think, for your exam skills, is write down the question, and it forces your brain to process what you've got and maybe notice things which just on skimming over you haven't spotted. In this case though, notice that to get rid of y, I have to get, well, it's very useful to be able to get what y equals in terms of x. So that's what I'm going to do first from equation 1. Let's call these 1 and 2. You don't need to label them like this, but for the sake of this video it might be clearer. I'm going to put, in equation 1, I'm going to put the 5y on the left hand side, so I can begin to aim for y equals. And I'm going to put the x dot on the other side, so minus x dot would turn up, and then everything else is as it was. And notice I'm writing these in the order of derivatives, so I've got an x dot, then an x, and then the term with no x's in it at all. It's just helpful to have some sort of regular routine that you expect here. I would also then realise that y is just a fifth of all that. And I wouldn't necessarily write all the coefficients separately, I'm just going to put a fifth out the front because it's easier to get rid of later on. So I hope this makes sense to you. This is a good step because now we've got y in terms of x and its derivatives. There's no y's on the right hand side, and that will be useful because I can, every time I see a y in a different equation, I could just sub in that horrible looking thing. Looking at the other equation, number 2 over here though, you can see that to be able to sub in, I also need to know what y dot is, but I can do that down here by differentiating this line. The fifth would stay as it is, everything else just gets differentiated, and it turns out to be remarkably easy to do this. I do have to do some real differentiation here on the function of t, and that's going to become minus 18 e to the minus 2t. And just check you're happy with that. So I can use these two things in this equation. I can swap the y's and the y dots. So I haven't used equation 2 yet, but now I'm about to, and it's no surprise that I have to. I need to use both equations somehow in order to get this second order equation out. So let's rewrite equation 2 by replacing y dot and y with the expressions I've just got. And it ends up being a lot of writing. But do it carefully and do it right. You won't go too far wrong. This module definitely repays some care in algebra, so you need to be speedy but accurate. On the right hand side I've got an x, because that's where it was, and I've got minus 4y. I'm just going to write minus 4. Realise that y is this thing here, so I can write that as 4/5, and then copy out the bracket. You've got to be careful with the dots if you're using x dot notation, that the dots are clear to the examiners and to you, so you don't copy them out incorrectly. And once you've done that, it often feels like you've finished, but don't forget there's another bit over here. A lot of people forget to do that because it feels like you've done the hard work, but that 3e to the minus 2t is still there. Okay, it looks messy, but it is an equation with only x and its derivatives and the functions of t, so it's promising. My first instinct is to get rid of the fractions, so I'm going to multiply everything by 5 and write it out again. Take it slowly, don't be afraid of a little bit of writing, and you'll go probably more efficiently through this. The x does need to be multiplied by 5, the minus 4/5 becomes minus 4, I'm going to expand out the bracket as well, so I'm going to get a plus 4x dot, I'm going to get a minus 8x, and I'm going to get a minus 4 times 9, which is 36, e to the minus 2t. And on the end, multiplying by 5, don't forget, it's 15 e to the minus 2t now. Almost there. I think I've got an equation which is beginning to look promising. I'm going to collect all the x's and its derivatives on one side. Since it's negative over here, I'm going to put the x double dot on the right hand side because I'm after a positive coefficient of x double dot from up there. Which means if I want the x's on the right hand side, I want the functions of t on the left, and I've got minus 18 and I've got minus 36 plus 15. Adding them together on the left hand side, minus 18 minus 15 plus 36, all told gives me 3 e to the minus 2t. I'm feeling good about that because I've just spotted that. Always worth checking where you're going. On the right hand side I'll get an x double dot, it was negative on the other side. I'm going to take away 2x dot, and I had 4 already on this side, so I'll have 2x dot left. And finally I've got 5x minus 8x, altogether that's minus 3x. And that's it, and that is the equation they wanted, so I'd finish that by saying as required. It may be worth including another step showing how you're adding these things together, but I don't think anyone can argue with the working as it was written here. It doesn't matter that you got it the wrong way round. These things are equal, so they are the same, and so one thing being the same as the other is the same as the other being the same as one thing. I hope that makes sense. Getting to this stage is almost always the first step, and they give you 5 marks for it. And you haven't had to do too much solving of equations, you've just done a tiny bit of differentiation and a fairly chunky bit of algebra, but only in collecting coefficients together and things. Let's have a look at part 2, because it's very predictable that they're then going to ask you to solve the thing. Even if you can't do part 1, as I mentioned, you should be able to do part 2. It's a second order differential equation, so this is the standard skills. The first thing to do is get your auxiliary equation, which is the what happens, just as a reminder, if you guess that the solution is x equals something to do with a e to the lambda t. You don't need to write that down. What you can get used to is the fact that it just jumps in with a lambda squared plus 2 lambda minus 3. And it equals 0. Remember, we're solving the homogeneous case first. We'll sort out the right-hand side with our particular integral. Solving this equation is pretty straightforward. I think it factorizes neatly here. Lambda lambda. Don't be afraid to complete the square if you can't factorize straight away, but I think this does factorize. I need a 3 and a 1, and I think I'm going to need a plus 3 and a minus 1. So lambda is 1 or minus 3, leading to a complementary function, which is the solution to the homogeneous case of x equals some constant e to the t plus some other constant e to the minus 3t. That is my complementary function. So far so good. I need a particular integral now. I'm going to go up here and do this. Let's try something which looks like the right hand side. So I'm going to try x equals alpha e to the minus 2t. I should always check that this function isn't the same as something in my complementary function. If it is, you'd have to do something clever. In this case, you'd have to try x equals alpha t e to the minus 2t if e to the minus 2t turned up in the complementary function, because it wouldn't work. Dumping this into the left-hand side would give you 0, and we want it to give us something, not 0. But in this case, we're fine. So that's just a little aside about watching out for that thing. If x is alpha e to the minus 2t, then x dot would have to be minus 2 alpha e to the minus 2t, and x double dot would have to be 4 alpha e to the minus 2t. And I can put those into the equation, and I'd get 4 alpha. I'm actually going to skip all of the e to the minus 2t's, because they will be in every term. That's just saving a bit of time. So plus 2 times whatever x dot is, which is minus 2 alpha e to the minus 2t, remember that would be there, but I'd cancel it out, and minus 3 times alpha e to the minus 2t, which is just x, and that's got to equal 3 e to the minus 2t. Confusingly, then I have written e to the minus 2t, so let's just put that in order for me to cross it out. You can see why I was reluctant to write it, but my instincts took over. Altogether then, we've got 4 alpha minus 4 alpha minus 3 alpha equals 3. These two have gone. Minus 3 alpha equals 3. Alpha, I think, must be minus 1. Which means we have a general solution. Notice my 4 two-letter acronyms: auxiliary equation, complementary function, particular integral, general solution. This is a kind of a useful stepping stones to look for when you're doing this. But I'm now ready to write down the complementary function plus the particular integral, which is going to be a e to the t plus b e to the minus 3t minus e to the minus 2t, and that comes from putting minus 1 in for alpha. So that is my general solution, and worth apparently 8 marks. Looking at part 3 then, it is no surprise that having solved the differential equation for x is that we now need to deal with the y's, which we haven't done yet. All we did was get rid of them to start with. And in order to do that, let's grab the general solution for x. And there is the general solution for x. We also might need to use the rearrange things we had before to sort out this y. So jumping back a bit here, you might need to spot, in fact going back 2 slides, that we had a useful equation for things involving a y. So we in fact actually had the equation for y right here. So I'm going to grab that as well. So there we have our y equals equation, which we got from rearranging that very first line. But it's very useful now because since we know what x is, we could find out where x dot is, and with those two things we could put them in here to get what y is. And this is always the way it seems to work. X dot is therefore going to be relatively easy to sort out. I just differentiate the previous line. I'm going to get a e to the t. I'm going to get minus 3b e to the minus 3t. and I'm going to get plus 2 e to the minus 2t. So that's x dot. With x I can put them in, I can begin now to write down what a is. Not a, sorry, y. So I'm just going to write down a fifth and start plugging all this in. It's going to look messy at first, but I'm just expecting to have to tidy it up. A e to the t minus 3b e to the minus 3t plus 2e to the minus 2t. That's the x dot, but all of those were negative, so let's just make sure they are negatived, if that's a good word, which it's not, never mind. Plus 2 lots of x, so that's 2 lots of a e to the t, plus 2 lots of b e to the minus 3t, minus 2 lots of e to the minus 2t. Make sure you get the 2 in all of them, and don't forget the last bit. Again, easy to forget that. I've got 9e to the minus 2t here, and this is still all in the bracket. Now it's just a question of tidying up, which is a little bit daunting. I'm just going to leave the fifth out the front for a moment. Let's collect together the e to the t's. Looking at that, I've got a minus a from here. What else have I got? I've got 2 a's here. I've got any other e to the t's? I don't think so. Let's have a look at the e to the 3t's, or rather e to the minus 3t's. I've got a 3b from here. I've got a 2b here, and I think that's it. And then finally I've got the minus 2t's, the e to the minus 2t. If in doubt, write a plus and then just deal with the signs, but it possibly looks like I could have been more efficient, because there's a minus 2, and another minus 2, and the plus 9. But you can see I've just done sort of by factorising out the individual bits, and now I think I'm ready to finish this off, because this is a fifth of minus a plus 2a, so that's just a e to the t. I've got 5 b's, excuse me, and I'm thinking that's good because it will cancel out neatly when I put the fifth back in. And finally I've got 9 minus 4, so I reckon that's a 5 e to the minus 2t. So tidying this up now, final line. Let's do it separately if it's going to be our final answer. Y equals a over 5 e to the t plus, keep the b, e to the minus 3t plus e to the minus 2t. And that is our general solution for y. It is important that you do it this way. What obviously you could do is go way back to the beginning and actually come up with an equation, a second order equation for y, just like we did for x, and solve it to get an equation for y. And that would be fine, except that the arbitrary constants, like the a and b I've used in my solution, would be probably different. And so you can't do the two things separately and expect the constants to come out the same. And if you want to use the same constants in the same two solutions, which you need to do in order to eliminate it later on, you need to derive this y solution from the x solution, so that you carry these a and b constants with you, and they are definitely the same constants. But that is our general solution, and that's going to get us another 4 marks on the way to smashing this question completely. So moving on, part 4, and this is almost always the way, having got the general solutions, they give us some more information which tells us that we can find the particular solutions. They say initially here, please recognise this is an important word implying that t is 0 at the beginning of your clock. Initially, we can now find the particular solutions. Let me just grab the solutions we got from the previous slides. Okay, so with these solutions we can actually get the values for a and b with the information. First of all, let's use the fact that x is 0 when t is 0. And that means I've got 0 is equal to a, and the e to the t is just 0, is 1, plus b, e to the minus 3t is still 1, and minus 1, because that's the last e to the minus 2t is still just 1. That's pretty useful, but I can't actually get a equals or b equals out of that. I need to also use that t is y when t is 0, and from the second equation there I've got 2 is equal to a over 5 plus b plus 1. So I need to eliminate one of these things to get a and b. It's rather obvious that I could add these things, subtract these things one from the other. Let's do the second line minus the first line, and I'm going to get 2 on the left. I'm going to get a over 5 minus a, so I think that's minus 4/5 a. The b's will cancel. I'll get plus 1 minus minus 1, which is 2, and immediately we get that 2 equals something plus 2, so I think a must be 0, which is a relief. And that straight away tells me from this one that b is 1. So we have some nice, neat, particular solutions, which are x equals a is 0, so we've just got e to the minus 3t, minus e to the minus 2t, and that y equals e to the minus 3t plus e to the minus 2t. And those are rather neat solutions. It's amazing when you actually get the constants solved that these horrendous things you've been dragging around and messing around with constants for a while end up being rather simple. But getting to that stage is a rather nice 4 marks. So moving on to the final question, part 5 says describe the behaviour of these solutions as t heads to infinity. It's important that you recognise that these questions are easy if you know about the behaviour of functions. So in particular, functions like this with a negative power, when that negative power gets very large, this is going to be essentially 0. And I just think you need to show the examiner that you know that. So what you could probably write is as t goes to infinity, e to the minus 3t goes to 0. And so does e to the minus 2t, in fact. You could just mention that, but then it's rather obvious that x will therefore go towards 0. And for the same reasons, y will go towards 0. It may be that you feel like in order to definitely earn the marks, you should figure out whether this is going from above or below, and I'll let you ponder that. What you can always do is put in t equals something large, say 100, and work out whether you think this is coming towards 0 from above or below. It's rather obvious that y, if you look at the function, is always positive, but if it's always positive and heading towards 0, it's definitely heading from above. And it may be a little harder to figure out what's happening with x, but if you realise that if t is very large, then e to the minus 3t is even smaller than e to the minus 2t, because the bigger power you get when it's negative, the smaller it is. So you've got the bigger thing being taken away, so it's going to be negative. So this one actually heads to 0 from below. But I'm pretty sure the mark scheme would still give you the marks even if you didn't say those things. It's possible they could ask for it, so be prepared to reason about that. So that's the first bit. It then says state with reasons whether this behaviour is different if the initial value of y is just less than 2 and the initial value of x is still 0. So what they're doing here is they're changing the initial conditions they've offered you. So it's almost like you have to go back a couple of steps. And to do that, let's just grab the solutions before we found a and b. So nice and small there are our solutions with the a's and b's left in them still. And what's important to realise now is we've got conditions where x is 0 when t is 0, but y is just less than 2. And you'll remember that when we put that first equation together, we got 0 equals a plus b minus 1, and we got the second equation. Well, this time we're going to get, let's say it's 1.9, because that's a bit less than 2, equal to a over 5 plus b plus 1. And last time we did this, when we did the subtraction, we ended up with 2 equals something to do with a plus 2, and we got a is 0. And this time we won't. So I think the easiest way to sort this question out is to realise that when you solve it, you could either solve it with the example like I've done here, or just immediately realise that this implies that a is not equal to 0. And if that's true, then we've got the x equals something e to the t plus some stuff, and y equals something a over 5, in fact e to the t plus some stuff, and this term does not have a negative power. So what you need to spot straight away is that as t goes to infinity, x and y will go to infinity now, because that term is growing instead of shrinking to 0. So it makes all the difference. A tiny, tiny change in y, even if it's just less than 2, suddenly means these solutions don't decay to 0. They actually grow exponentially as t gets bigger. So I think to get the marks here, it says state with reasons whether this behaviour is different. Yes, it's different, since e to the t term is present, you should probably say useful sentences. And then you could state this thing here, that x goes to infinity and y is going to infinity as t goes off to infinity. And that is actually the end of this exam question. Let's quickly look back at the whole question again to remind you what happened. This is the overview as we had before. Notice that this is going to be like all the other questions like this. They give you 2 equations. You eliminate one of them, or one of the variables, to get a second order. You solve it, you use it to solve the other variable, get some conditions, use the conditions, and figure out what happens over time. And I think this is all relatively straightforward if you can solve second order differential equations. We're going to finish this video here. There are going to be other videos available on the other questions in this 2010 and 2011, and on the other topics in the differential equations. My name is Ben Sparks. See you on another video.